Hi, my name is Geir Eide. I am the Product Marketing Manager for the Silicon Learning products at Mentor Graphics. And we are here at ISTFA this year to showcase some of the products in our Tessent product family. And this is a product family that consists of several products that are used to insert test structures and generate test patterns for semiconductor devices. And traditionally, test has been about pass-fail, about determining which devices we can ship to customers. But it turns out that the fail data that we can get from these failing devices contains a lot of very valuable information that we can use to understand where these defects are located, but also, maybe more importantly, to understand what's the big picture, what's really going on, what are the systematic defects, what are the critical design features even that we want to be able to analyze, and what we call diagnosis products and statistical analysis of diagnosis results can allow us to get to this data based on just the test results. And here at ISTFA we are focused on two products. The first is what we call Tessent Diagnosis, which is our diagnosis product that allows us to basically turn fail data into defect locations and defect classifications. So we get a result for each defective device that we want to analyze. Now, Tessent Yield Insight is the second piece of the puzzle, and Tessent Yield Insight can be used to take a set of diagnosis results and analyze these to allow us to understand the underlying root causes and allow us to find systematic defects and help us select the best devices, the most relevant devices for FA. Again, diagnosis basically consists of a process where we take the fail data, the production test patterns, and the design information, and from that we get the defect locations and also the defect classifications, so basically information about what type of defect it is that caused the failure. And what Mentor Graphics is famous for is what we call layout-aware diagnosis. And this basically means that we take the layout information along with the logic representation of a design, and that allows us to get a more precise, more accurate result, and also to better differentiate between different types of defects. So we, in effect, get more data about the defect. Now, in Tessent Yield Insight, we can take these results from many failing devices and analyze them and make more sense out of the set of results. And we have different ways to analyze this data. We can, for instance, look at die level and wafer level heat maps. We can see if there are clusters that are associated with specific defect properties. And the most revolutionary capability that we have in Yield Insight is what we call Root Cause Deconvolution. And that's a way to get rid of some of the noise that exists in the diagnosis data and get very accurate defect Paretos. So the fact of the matter is that no matter how sophisticated of a diagnosis tool or diagnosis solution that you have, there is some ambiguity in the data. You might see that the tool, for instance, will say that there could be multiple defect types that could cause this particular failure. It can't quite make up its mind. And the root cause deconvolution technology basically uses statistical enhancement to combine machine learning and design statistics to eliminate this noise and give you a very accurate defect distribution. And this can be used to basically allow you to very quickly compare results from multiple lots. This is something we, for instance, published in a paper last year where we very quickly got defect distributions from different lots from different process conditions. We could get this without doing very expensive and time-consuming FA. So we're going to take a quick look at Yield Insight and also look at the diagnosis results. And I'm going to start out by looking at basically telling you what I'm looking at here. So in this case, we have diagnosis results from 950 failing devices. So we ran Tessent Diagnosis on fail data for 950 failing devices. And if I look at the big picture, I see that I have data from 3 lots. I have data from multiple wafers, and if I stack this all on top, now I see that I have a couple of clusters here. There are a couple of areas where I see population or a larger concentration of defects. And what we would like to do in the analysis is to understand what's really behind these clusters. So from this RCD analysis, the root cause deconvolution analysis, I get this very nice Pareto here that basically tells me that the most dominant defect type in this material is route 2 or metal 2 opens. So about 23% of the devices fail because of metal 2 opens. So one thing I can do, for instance, is to now look at find a device that has the highest probability of failing for that particular defect type, so for a metal 2 open. And this would be like an ideal candidate for FA because the tool believes that this is the device that has the highest probability of failing due to this particular defect type. So I can now go in and pull up the diagnosis report for that particular device, that particular die. I can look at this in the actual report, or I can also open this in a layout viewer and basically zoom in on the part of, this is an open, this is the part of that net where the tool believes there is a metal 2 open. So I know that this is now the most likely, the candidate that's best for failure analysis for representing this particular type. Now the other thing that I saw in my Pareto here is that there were some of the bars that were displayed in a different color. And what this means is that there's a zonal sensitivity associated with this root cause. So if we click on this, what we see in this wafer map, which is basically shows us like intensity related to the probability of devices failing for this particular defect type. And we see here that there's a very large or very visible cluster in the center of the wafer, and this bar basically shows us how much more devices we have in this part of the wafer compared to what would be considered normal. So this basically tells us that that cluster we saw initially is, when we looked at all the failing devices, is caused by this particular defect type. And again, I can go into my my table to find here the device that the tool believes has the most likelihood of having failed because of this particular reason. So this probability is not the same as the diagnosis score you might recognize from a diagnosis report. This is basically a statistically enhanced probability. But now in looking at this, the metal 3 shorts, I can again look at the diagnosis report for one of these devices, and I can look at this in the layout viewer and basically here find the location where these 2 nets are most likely bridged together in metal 3. So again, I can use this to both find the defect distribution and also find the best candidates for FA. So as we mentioned initially here, we're talking about Tessent Diagnosis and Tessent Yield Insight here at ISTFA. And thank you very much, and come see us at booth 209 here at ISTFA 2013.